one of the agencies called Research Executive Agency. And what they do is basically switch sides of the table. This is no longer the one soliciting funds for research projects, but he's the one evaluating those applications, tender applications. So they certainly appreciate his deep understanding of the subject matter, because he knows what sort of criteria he needs to look at to evaluate certain projects. So PhD you can pursue research, or you can leverage your subject matter expertise when it comes to say tenders or your projects. So these are basically the two main areas of combined research executive agency and the research center.
And then it doesn't go through ESO, it goes through...
Again, normally it does, but it depends. So the system is getting a little more complicated. So the more unique, the more specialist the profile is, the less likely it is that it goes through ESO. So if they really want to say two new staff who are into social science research or sociology or social anthropology or something like that, they're not going to go to so they can announce the tender rate and position, and they will just simply accept applications and evaluate that on a case-by-case basis. The selection process is more hard. They want to hire 10, 15, 20, 50 new staff in the field, then they will already go to ESO.
There is one question from an online participant. So the question is, how long are we on the reserve list once we pass the program as a process? Is there a better time during the CPD?
Right. Now, as I mentioned before, the ultimate goal of the ESO process is that you end up with a reserve list. And from the reserve list, you still need to be recruited. How long you're there and how long the reserve list itself is valid, but only 1 year is the result of a competition that happens every year. So if it's a generalist competition, the rule of thumb will be that it's valid for. If it's a specialist competition, it will be valid for longer, usually 2, 3, sometimes even up to 5 years. And within that time frame, you can be hired. So you could get a job offer that you're not very happy with, and you can decline. Or you don't get a job offer for a couple of months and you'll get it for 1 year, that's also a possibility. But as long as the reserve list is valid, you can be hired. And US Australia, these days, I'm not exact statistic, but something like 85% of those on the reserve list would get hired eventually. And US would about 15%. But sometimes they themselves, their life circumstances have changed, they moved, they feel really interested. So sometimes it does come from the participants that they can be hired.
Other questions? Yes, please. Hi, I would like to know, what are the opportunities for PhD students in philosophy and if it from India, in Europe? If you have a very question about PhD in philosophy from India.
Talking about that agricultural, now there's a lot of value there. And that obviously is finding which organization would be particularly that profile. And obviously there are a lot of organizations who have, whether trade relations, whether it's political issues with political given identical. Philosophy, well, that's a number one, because in this political and policy environment, I have philosophy might be a difficult stuff. To be very honest. But then again, maybe it's a research angle, maybe I don't know.
Okay, what about for corporations who are Canadian? Well, I think that unless it's not really a research angle, maybe might have any good they are investor or they try to look for jobs in Europe, different sites for jobs in the European institutions or European affairs, and I think that should be the last question.
Yeah, and I know it's late and not difficult. So I'm very happy. I'll send you, as a follow-up, I'll send you the link to the presentation, and I'll send you some links that you can tweet onto the channel, open position. So I'll send you a link to that one as well, and a couple of other websites that you can look at.
Surname, I have a sheet of paper there. I'm going to send the presentation and all the information that I'm actually going to share with you. And I saw one last question.
Yeah.
Okay, do you have time for one last question?
Just a quick one. Make sure, so every time you answer your questions, send it in. Great, will be sharing that with you. So if you have anything related to episode or careers, whether it won't answer very fast, but I will answer eventually. So
then I will last question.
What do you think? What will be the most developing part that you think of the institutions in terms of staff? What will be the most developing part if we're looking further the next couple of years? So it's one of the most developing. I think given the dynamics of European politics these days, I think the European Commission would always need to hire hundreds and hundreds of staff. I give you just one piece of statistic, I probably should include it in my presentation. But looking at the number of staff that's going to retire in the next couple of years, something like 40% of the staff will reach retirement age. So even if these institutions have no intention to expand the number of staff, even if they reduce it by 5%, is sailing hundreds and hundreds of staff, almost thousands of staff each year just to maintain their core operation. So commission is always a good employer to look at in the future. And also in national capital. So I think EU experts will be in demand because simply the dynamics of European affairs in all ministries of foreign affairs, justice ministries, trade ministries, and the like. So that's definitely a place to look at.
If we're able to throw something very light in, that decreases the entropy of the outside.
Okay, so we can test this. The lightest thing that we can throw in would be, let's say, an massless particle the size of the black hole. So that would have an energy, which is like 1 divided by the radius. And if we throw in a particle like that, then we can decrease the entropy of the surroundings by, about 1/10, roughly 1/10 of entropy. So we would like to see that we have increased this black hole entropy by about 1/10. Okay, so we can work that out. Delta F is equal to eta times delta A over G Newton. And then we can plug in for R using this formula. So erase delta R and put delta M times G Newton times 2. Okay, and delta M here is 1 over R. So if we plug this 1 over R in, that will cancel this R. This G Newton will cancel that G Newton. And we'll be left with eta. Well, at this point I should not put a equal, I should put a squiggly. This squiggly is less squiggly. Eta times 16 pi. So indeed we see that the change in entropy using this formula will be order 1. So as long as this quantity eta is too small, it looks like we're in good shape. So Einstein did not, using this argument, he wasn't able to determine the actual value of eta. But there have been later arguments, very beautiful work by Horacio Cassini and Aaron Wald, where they're trying to prove that no matter what you do, the total of the entropy outside and this black hole entropy will not decrease. And using the monotonicity of the relative entropy and some beautiful arguments, they're actually able to show that this will be true, provided that eta is greater than or equal to 1/4. So it's amazing that by thinking carefully about this original sort of proving the argument technically, you can actually get the numerical coefficient. Okay, so that's 1972. The next thing I want to discuss in 1974, this was the year where Hawking made his calculation of the black hole temperature, which is 1 over 4 pi times R. I'm not going to discuss this in very much detail, although later we'll be able to see how you can derive the temperature of the black hole. But we can use that to get this coefficient by using the first law of thermodynamics, dm equals gdf. So we can just use this formula here. Here we worked out dx in terms of dm. So dm is equal to, I'll put in 1 over 4 pi r for the temperature. And then we plug in this formula for df. Get data times 16 pi times dm. Okay. And if we cancel the 16 pi and the 4 pi, we find that data has t equals 1/4. So this completes the derivation of the black hole entropy. And this was the moment when the actual coefficient was determined. Although people had thought very hard about it, they could have determined it earlier. Well, they could have determined this inequality earlier. Okay, so this sort of started a very long and beautiful relationship between black holes and thermal systems. I'm going to skip over most of it. In particular, I'm going to skip about 20 years, which included the story about the membrane paradigm, and it actually included a third derivation of the black hole entropy using gravitational path intervals. I'm going to skip ahead to ADS-CFT, because this really changed the way people thought about this. Before, the idea was somehow that black holes and thermal systems had some somewhat vague relationship. You could think of a black hole as a thermal system in some cases, and that was a little bit helpful for thinking about black holes. ADS-CFT turned this around because this was a precise identification between black holes in certain systems and particular strongly interacting large N quantum field theories, which are difficult to analyze. And now the flow started going the other way, where you could do a calculation using a black hole and learn something about a very difficult problem, which is strongly interacting field theory. So for example,
two types of things: thermalization and chaos. There's another aspect to real-time dynamics which has to do with transport. And I'm not sure if Sean Hartwell's going to talk about this. Historically, at certain lectures, he has talked about transport, so I'm not going to talk about it. But so in the lecture today, what I'm going to do is give a little bit of an overview of what we know about thermalization and chaos in thermal systems without using black holes. And then in the second part of the lectures, I'll show how to calculate aspects of thermalization and chaos using black holes. And then actually for the third part, I haven't completely decided yet about whether I'm going to talk about a bound on chaos, which was originally inspired by thinking about black holes, but it's just a statement about quantum systems, or whether I'm going to talk about what I view as sort of a third potential offset in this connection between black holes and thermal systems, which is this amazing model that Ikhaev has developed, which is an exactly solvable, strongly interacting quantum system, which is probably dual to a black hole. And this thing has the potential to start the arrows pointing the other way again, where we use properties of thermal systems to understand black holes. I find it really exciting. So that might be something that I talk about towards the end. Okay, but under thermalization, there's actually two topics I'm going to discuss, which is the behavior of support functions and relaxation near equilibrium, and also questions. Okay, so this is the plan. And before I start, let me just see if anybody has any questions about the plan, or what the words mean, or why we're doing this, or anything like that. Oh, I should ask you guys some questions, because that's not very much about you. One question that occurred to me was, I don't know how much you guys know about black holes, so who knows what a Penrose diagram is? Okay, who doesn't know what a Penrose diagram is? Okay, most people know what Penrose diagrams are. Okay, I have some other questions that I'll ask later. Also, you should tell me, of course, if this is going too slowly or too fast, whatever. I'm happy to adjust it. Okay, so the most basic diagnostic of thermalization is to take a system which is near equilibrium and then perturb it by a very small amount to see how it relaxes back to equilibrium. The expectation value of the thermal state of these operators or phi of some operator for the series. In general, we could have different operators here, but I'm going to take the case where they're the same operator. So here we're writing this as an expectation value in the thermal state. But sometimes it's convenient. This is an expectation value in a mixed state, have an expectation value in a pure state. And it's not, for some reason, it's not as widely understood as it should be that the thermal field theory and the thermal states and quantum mechanics are not necessarily mixed. The central features of thermal states are that we're talking about relatively high energy states in the spectrum of energy states, where we have an extensive amount of energy in the system. It's not so important that it's a mixed state. So, for example, we could get almost the same answer if we take an expectation value and a pure state beta, which I'll define in a moment, of phi g phi 0. And here, beta can be under suitable conditions, it can be basically any state with the right energy statistics. So in particular, we would like to have that the expectation value of the Hamiltonian in the state beta should be equal to the thermal expectation values. Okay. And actually, it's important that we would like higher moments to agree as well. The idea that these things should be basically the same is part of the story called the eigenstate thermalization hypothesis. Is this something that people are familiar with? You raise your hand if you know about the eigenstate thermalization hypothesis. Okay, this is not like Penrose diagrams, so maybe I'll say a couple of words about that. So this is an idea. Oh, it's roughly what I said. The idea is that, actually the more precise version of the idea is that we look at energy eigenstates of a interacting system, of a suitably interacting system, then those energy eigenstates will locally look indistinguishable from a thermal state. In particular, if we take an energy eigenstate E, and we form the rank 1 density matrix out of this thing, and we trace it over the complex, to compute the thermal density matrix of subsystem A in its energy eigenstate. The claim of the eigenstate thermalization hypothesis is that this density matrix will very closely approximate the trace over a complex of the thermal density matrix, provided again that we take the right energy here. Okay, does this make sense? Are you guys familiar with this idea of tracing over part of the system and getting a density matrix on the rest of the system? I'm going to show of hands whether you're comfortable with that. Okay, somewhat comfortable, somewhat uncomfortable. So here what I mean is we imagine that the system is an extended system with many sites. Okay. And we could consider one of two types of states here. We could have the thermal density matrix on the whole system, or we could have this energy eigenstate. And then if we look at the density matrix on a subsystem A, the claim of the eigenstate thermalization hypothesis is that